Sabina, maybe we'll wait one more minute, but start whenever
Yeah,
you would
let's
like.
wait a little. We still have
Yeah.
some time.
Yeah, we're recording.
Okay, I think I get started because we have a lot of information to cover. So this is the third lecture in the series of lectures. And today I'm going to talk about survival analysis, mastering the essential. So actually survival analysis is my favorite analysis. In addition to simple models, we're going to discuss today, there are more, of course, more sophisticated statistical survival analysis model, like longitudinal model, multi-state models, and so on. But we use it as this type of analysis a lot, especially in health data. Yeah, measuring something where time to event is very important and event is also important. So I'm basically going to talk about Kaplan-Meier plots and survival analysis. We're going to use the same data set I used before for logistic regression. So if you didn't listen to it and need some rationale, you can review it later on our YouTube channel. It's already available. But basically, to summarize, for those that did not attend the previous lecture, basically we used some data with logistic regression and we couldn't tell a story. There was not much story. So I thought like, oh, if we will add to what we already did time to event, yeah, to see how time to event affects the model, maybe our story would be better. So basically, this is what we're going to do. So of course, objective understand survival data, learn unique characteristics of survival data, including censoring and time to event outcome. It explores the core methods and like most used in medical research, it's Kaplan-Meier estimates, log-rank test, and Cox proportional hazard model. Develops the ability interruption survival cross hazard ratio and statistical significance. And also, as for any model, to look at the assumption and see what we could do with them. And the story here, so classically in actual life, Cox proportional hazard model assumption rarely hold. And we need to decide if what we see in assumptions, like in our check, if it's still fine and passing some kind of minimal threshold for us to continue with this model, because there is no perfect situation. So if you remember our detective, he basically last lecture tried to look at Barn mortality prediction modeling on binary outcomes that was a life and death. And he used logistic regression and he showed some results, but unfortunately there was not a lot of story. And of course he said, okay, maybe I can improve the analysis and find something more interesting if I switch from logistic regression to survival analysis. So basically what we did before, we have our outcome as yes, no, died or survived. And we try to estimate odds of dying to see what characteristics from the sample, like sex, inhalation injury, how if person was in ICU, had surgeries during the ICU stay, if those affected the chances of survival or risk of dying. But to follow the clues over the time, we need survival analysis. And this is a powerful set of tools that were designed not answer, not just who, but when. So time here, timeline is important. With Kaplan-Meier's curve, you can do descriptive analysis and basically see who is dying more and how fast are they dying. Yes, for example, based on the difference between multiple lines, if you do stratified Kaplan-Meier analysis, you can see not only that there's difference, but the change in the line, the shape of the line can show you that it's not necessarily who is dying more, but how fast they're dying or any other outcome. What are Kaplan-Meier curve? Kaplan-Meier curve is also known as product limit and scintimeter, and it's not parametric test. Yeah, we don't care if you have outliers, we don't care about anything. Basically, we only care about total number of patients, either in overall or in each strata, and in each time point who failed. Failed in this case, meaning who died. Yeah, so it's if we're talking about survival plot, because you can kinda use Kaplan-Meier estimator to calculate cumulative incidence, but the mathematics behind it will be slightly different, so we're not going to go into it today. So we're talking about survival analysis. So basically, we're starting with probability of 100, means everyone is alive, everyone survived in time point 0, and when patient dies, it means the probability drops. Yes, because now in total we have less people, and some people left the study because the outcome happened, in this case is death. So basically, the Kaplan-Meier, as you all know and probably so, it's stepwise survival curve that is drawn based on the events. So basically, how is visualization? We usually have time on x-axis and survival probability on y-axis, and curve drops at each event. So basically, it's like a step, and each event, our curve will go down. A higher curve means better survival, so basically better chances of survival. And we can do it for overall population and also do by multiple stratas, but our multiple stratas can be only categorical variable. We cannot do Kaplan-Meier by age. Technically, we can do it, it will going to run, but you have many lines for each age group, so it will be like very not appealing, but actually for some of the analysis, not for final presentation, but to see, I sometimes do it by a lot of groups, like individual age. Yes, just to see like basically if there is something different, but usually for presentation for the papers, we don't do it. So here is the example. Actually, this is example from our actual data. And I try to build a survival curve for based on Kaplan-Meier estimator, product limit survival estimates for full population. I didn't divide it by the strata. So basically, here on the left side, you have part of the output. I'm going to show you how actual SAS output looks. So basically, I only picked up the point where failure happened. So when people died, and each time point person died, this person was cumulatively added to number of failure, and the total will be number left. So after we calculate number of failed, we do basically previous total minus those that failed and censored, and we'll get to the probability on next point. Yes, so I highlighted here in red. So basically, at day 1, 8 people failed. So basically, they probably had very severe injuries. They died almost right away. So 8 people died right away. So now total number changed from 793 to 785. And we, by dividing 785 by 793, we got the probability. This is survival probability. And probability of failure, it will be in this case 1 minus survival probability. But if you can see, when we get to the point 2, we have 12 people failed. But our total is not 785 minus 12. It's lower, it's 696. Why? Because we're not adding those that censored. Censored means that they survived and they got discharged from the hospital. Yes, but so for the total is affected by number of failures and also number censored, because we're not following those people anymore. But in denominator, on top of our equation, we will have cumulative number of failed. Censored will not be included. So this is why I'm showing the next slide. So basically, it's how the same output that was like combined only for the points where a failure happened. This is an actual SAS output. I don't know, R maybe like maybe in R you can see the same. I never used Kaplan-Meier in R, so I'm not sure. So basically, it's exactly the same. LOS, it's length of stay in the hospital, basically time to the charge. We can see that at point 0, survival probability is 0. There's number of failed. Failure is 0, survival error is 0, number of failed 0, and we start with 793. You can see here 1 with the star. 1 in the star means that it's still time 1, but non-events of failure happen. Those basically you censored people. So we saw that, so if you look between 0 and 1, yes, from 1 to probability of 0.9899, you have multiple ones. So basically how SAS structure it is structured for each person. So at second line, 1 person's failed. At the same time, you have additional person failed, so it will be 2 and so on. But when you can see when it's 1 with a star, it's still people that censored, the number of failures is not changing. It's continue to be 8. But the number left is changing by 1. It means those are the people that censored. So they left hospital after discharge, and we actually don't know what happened with them over. So here actually I highlighted with blue lines the time point 2. Yes, so basically we have 696 people. It means including those that censored, and we have 12 that failed. So I did simple calculation. We have 8 people from 412 failed, but if you do the calculation, at this point, 85 people were also censored. So basically they left the hospital because they recovered or everything was fine with them. So this is how the output looks, and I thought it's very important to show you the output because it's actually showing you how the computer calculating. So basically, it's including each person for each time point, but it's only going to include the probability of survival and failure at the last person that failed and same time point. You can see after that there is 2 with star. It means we have 12 people that failed, and after that everyone is going like 696, 695 and so on. Those will be out censored at time 4, 2 or day 2. So now we need to talk about something very important for survivor analysis. It's basically what is censoring. As I said already, for this specific situation, censored patients are those who survived and were discharged. And in this case, we calling it right censoring. Why it's called right censoring? Because they discharge, but if our outcome is death, we don't know what happened to them after they discharge. Maybe someone discharged and died from sepsis 2 days later and never admitted to the hospital back. The only information about those people, we know that, for example, the red line here in the figure, it's an event, it's failure. So someone failed on date 5 and we calculated in failure, but you have additional persons that discharge on day 8, and we don't know what happened after the date. Maybe in day 8 and 5, he fell off the stairs and died. We don't know. It's why we call it right censoring. I'm not going to put too much attention on it, but there is issue. Also, there is different scenarios when people get into our study. For example, in this specific case, we calculate in time 0 time when they admitted to emergency department or came to the hospital. But for example, if you do something like clinical trials and look for start, there can be delayed start. For example, if you remember for COVID vaccines, yes, they say that you need at least 2 weeks for vaccine to start working. Yes, so you technically cannot measure, you cannot measure those that got sick with COVID after vaccine within first 2 weeks. Yes, because the vaccine still not didn't start to work. And basically whatever people that you count as sick, they're not sick because vaccine didn't work. They're sick because vaccine is still didn't start working properly. Yes, so this is kind of says delayed start. So when you do your analysis and you do study design, in 99% of the cases, we will have like right censoring in the survival analysis, but a small percent of the studies, you also need to look on the left and see how your people enter in the study. Additional exam, for example, pregnancy. Yes, the person come to the hospital and or to the doctor, and based on the pregnancy test, the person is pregnant. Yes, but doesn't mean that the person become pregnant on this day. There is a certain period before this person become pregnant. But for our study, people can come to the hospital with different start time, with different time. So someone came on week 3 of the pregnancy, some come after the first week of pregnancy. So you have here you have delayed start, but also for different time periods, and there is a way to incorporate in your analysis. It's like much more sophisticated, but you also need to put attention how you start your survival analysis. But this is not related to the specific presentation, because here the time 0 is like person got an injury, come to the hospital. From the minute they came to his hospital, we're following them up to discharge, and we don't know what happened for them after the discharge. So here, like example, how Kaplan-Meier plot, we're going to look by strata. What it means strata by categorical variable. So here I show the survival curve by sex, by biological sex, female and male. So here, based on this plot, what we can see, the probability of dying for male is much lower than for female. Also, female die faster. Yes, this like the steps for female, the blue line, go down much faster than for the red line for male. It means in this, for example, if you look on day 100, I don't know, 140 approximately, a lot of people died at this time period because the step going down like in the perpendicular line very stiffly. And for male, like, yeah, people died, but it's very, very like shallow, and the steps are much lower. So it means that not only the probability for females die it's higher than for male in this case, and this is supports what we got from our logistic regression analysis, but we also here see the timing when they die and how many of them died in each time point. So for example, in the beginning, you can see like in first days, there is the lines almost overlap, but later, approximately after day like 30 or 30 months, is the male going like really shallow and female die much faster. Yes, this is what it's telling for us. So based on this plot, we can calculate probability of dying. For male, it will be 0.21, and for female, it's 0.54. So, but here we would like to compare. We say like, yeah, we have the difference. Look, that there is a huge difference between by sex, but we want to see if this difference is meaningful or statistically significant. And how we're going to do it? For Kaplan-Meier plot, we're going to use log rank test. And computer calculates it like SAS when it's calculating Kaplan-Meier. It's give you several probabilities, but log rank test is most commonly used. So you will have probability. And in this case, the probability is 0.12 if you round it. So basically we say, oh, the difference is really huge, but it's still not significant. We would expect that such difference will be significant. And I'm going to explain you the rationale why it's not later. So in here our detective said like, yeah, I expected it will be statistically significant, but it's not. So what's going on here? So now I'm going to explain you what's going on here. So this is different example. And I created this example like it's fake data, but I did it on purpose to show you how to different plots with different number of events can give you significant or not significant result. So it's so significance for log rank test. It's very sensitive for your total sample, but it's also very sensitive for number of events. So here I have patients in two groups. It's patient in risk group A and risk group B, assuming they receiving different medication for bone marrow transplant. Yes, and in each time point, we measuring how many died every 3 months, and we know how many people died in each month, and we also can calculate simple survival probability here. Yes, and so here I have the table and say months 1, 0, 3, 6, 9, 12. And we need, in order to calculate log rank test, we need as like chi-square test and some other non-parametric tests. Basically, we comparing those observed tests and expected tests. And there is a way to calculate based on the formula expected days. So in our case, E, it's expected number of deaths, and O, it's observed. So basically what we see and what we can estimate based on the formula. And on the right corner, I show you how it's calculated. Yes, and on the bottom, we see what each of the letters in the formula are. So basically what we're going to do, first, we calculate what is expected death. And expected death is number of people died in time t in each month, multiplied by number of people in this group and divided by total in both groups. It's very simple formula, and I did the calculation, and I calculated expected deaths for group A and group B based on this formula. So what we're going to do next, as in any test, we're actually going to calculate chi-square. Yes, that's why it's expected and observed, because actually here we calculated specific chi-square test. And this is the formula of chi-square. So basically, it's observed and expected in group A divided by group A variance, and in group B by group B variance. And there is formula how to calculate variance. So basically, after all those calculations, I calculated that chi-square is 8.04. And here is the summary. Observed days in group A is 4, in group B 9, and I calculated expected deaths in group A 7.18, like based on the formula, and expected deaths in group B2, and we calculated the variance, and what it's here what we got. So, and now we need to compare. So exactly the same as we showed in other tests, degree of freedom will be our critical value. And then for this specific case, for the two groups, the degree of freedom will be 1. And if you look based on the book or in the computer chi-square for 1, the p-value will be 0.0 for 1. Based on this one, we can calculate the p-value is 0.0046. So it's statistically significant difference. So you say like, why? There we had 793 events, and here we have barely, I don't know, 20. And for such a small sample, here the results are significantly different. So we can try to explain it. So basically, I plotted based on this data, I plotted Kaplan-Meier curve for group A and B, and I put on the right side the plot that we created based on female and male from our actual data. You can see kind of the steps for group B here. It's like go down very fast, and for blue line, it's like shallow. Kind of the plots look more or less the same based on the shape and the structure. So for the sex, we received results are not significant. And here for group A and B, we suddenly received result like they're very statistically significant. So why it can happen? Here I try to explain the best way how I understand it. If many patients are censored, it means they discharge in a life as an out actual data. And there is small amount of those that had an event. Yes, it can affect our significance because majority of the people will be censored. And if you looked for the examples that I calculated for group A and B, less people were censored and most of the people had an event. For example, if I say, oh, it was bone marrow transplant for like patients that we give them medication based on compassionate grounds, the chance for them to die is very, very high. We actually expect that majority of them probably will die and small percent will survive. Yes, so here it's, so the test is very, very dependent on not only on sample size, how many people you have, but on magnitude of the event, how many censored and how many actually had an event. It also depends on heterogeneity of the groups. For example, our female are not the same. Yes, we can have female in different ages, coming with different type of injuries, with inhalation injury or not. We didn't adjust for all this for Kaplan-Meier because it's simple descriptive statistics, but our male and female groups are not homogeneous. They have we have different male and different female. Yes, so it can affect our calculation for simple descriptive statistics as well. So it's actually why we need modeling, because what we're going to do in the modeling, we're going to adjust our model for our available characteristics and see if all those characteristics combined will give us difference in death between two groups. So now we come into the modeling. And what is modeling? The simplest ever model that everyone uses, it's Cox proportional hazard model, or we call it just Cox model. The Cox model is not non-parametric and non-parametric. Cox model is actually semi-parametric regression. And most of them, more sophisticated models like longitudinal models with multiple events, actually, not all of them, but there is a group of models that it's more sophisticated, but still based on Cox proportional model, and all those models will be called semi-parametric. So what model is doing? This model used to assess relationship between time to event outcomes, such survival time, and one or more explanatory variables predictors. So basically, here we come in for more like inferential statistics that we not only describe in relationship between variables in our data, but we trying to understand full picture based on the variables we have available. Unlike logistic regression, which predict probability of events, and I already talked about it, Cox estimate the hazard ratio, the relative risk of the event occurring at any given time point. So basically, we can calculate relative risk in each time point. What was the relative risk of dying between female and male in point 1, 2, and so on. It does not require specific shape of the baseline hazard. And because we don't need specific shape, we don't say, oh, baseline hazard for the model should be coming from normal distribution. We don't put any mathematical function behind it. So it's our baseline hazard function is actually non-parametric. It's why the model called semi-parametric, because addition to the hazard function has some parameters. The model assumes that the effect of predictors is multiplicative. So basically here, if you remember linear regression, yes, for increase in 0.1 in X, linearly Y is going to change. Here we're not adding, we're multiplying. Predictors is multiplicative with respect to the hazard. So what multiplicative means? It comes from multiplication, which each factor scales the baseline hazard proportionally rather to adding to it. And actually it's from where the proportional hazard model means. So basically we can calculate some simple hazard function in baseline, and after that, based on this multiplication, we expect the proportional hazard is not going from baseline till time of death or end of the study. This proportion will be the same. Otherwise, it's not proportional hazard model. So here are some basic maths. It's how you actually write the Cox model. So it's written for each point t. So hazard function is each given time t for any predictor. X will be the baseline hazard function multiplied by exponential or actual exponential of a combination of predictor and their coefficient. So if you listen to my previous lecture about linear regression and logistic regression, you can see that what is in bracket for the exponential, it's actually our linear function, yes, beta 1x1, beta 2x2, and so on. But extent of having our intercept plus additional information. Here we have hazard in point, any point t, it's our baseline hazard multiplied. Yeah, so this is basically kind of like linear regression by multiply. It's not necessarily the same, but you can simplify it and see it like this. So the Cox model does not estimate baseline hazard directly because it is a semi-parametric model. Instead, the baseline hazard is left unspecified and it's estimated non-parametrically from the data. So basically, we're not saying the hazard coming from specific function based on our data, our baseline hazard depending on our data each time will be different. So here I give simple example, assuming we already did the analysis and we say the hazard of time t is hazard in time 0 multiplied by exponential and coefficient of h is 0.5 and coefficient of being an ICU is 1.2. So in this case, if h increased by 1 year, the hazard multiplied by exponential of 5 will give us 1.65. This means for h, there is 65% higher risk of the event occurring in any time points. And if we assume that our coefficient for ICU is 1.2, if patient was admitted to ICU, the hazard is multiplied by exponential will be 332. So this means ICU patient have 3.3 times higher risk of death in any time. So you can see here, same as for logistic regression, if continuous and categorical predictor variables explained slightly different. So here for age, it will be by 1 year of age. Yes, and we can calculate it will be 65%. But if we have like being on an ICU, not on ICU, it says, but by how much our risk in one group is high compared to the other. This is what multiplicative effect means. Each predictor scales the hazard proportionally. So here, like if you remember our model, we have different variables. So we have Bow index. It's the index created to measure severity of burn injury. And we had the confounder sex, age, inhalation, injury, yes or no, some comorbidities that they measured, hypertension, smoking, diabetes. And if you remember for logistic regression, I used like person was in ICU, yes or no, had surgery, yes or no, or was on ventilator. But here, because it's coming from the actual analysis I did, I actually decided, because it's time to event, I decided not use 1 or 0. I actually decided to use actual dates, because some people can be less time in ICU and some most time of ICU OR days, but it's actually number of surgeries, yeah, how many times they had the surgery during the stay. So when I adjusted to, like here I show an adjusted and adjusted estimate for Cox proportional model, and we can see that results compared to logistic regression quite similar. So our box is significant in more than one. So basically for each point of increase in bioindex, the risk of dying increased by, I believe, 7% here. So sex was not significant. Inhalation injury was slightly significant, and in confident interval is not overlapping 1. It means like strong estimates. Our comorbidities was not significant. Age was very statistically significant. ICU days were not statistically significant. Total number of surgeries was protective effect. Basically, we say surgeries help and reduce risk of death. And days of ventilator slightly increased. Days on ventilator slightly increased risk of death by 2% per each day increase. So after that, I did exactly the same as for logistic regression. I adjusted to all the covariates. And what happened here, exactly the same for logistic regression. Sex suddenly becomes significantly, but it was not. Inhalation injury didn't change. And our days on ICU suddenly is still protective factor. Like you saw it was like very close to 1, like not helping, not doing anything. But here we can see that ICU admission actually reduced risk of death in the end. And it's not overlapping 1, so estimates are relatively stable. And days on ventilator, when it was like very close to 1, now there is increased by 142. So basically, when I adjusted for it, our like model characteristic change, like relationship between all the variables change, and it's compared to logistic regression. I think here maybe because I used days and not actual events. Because actually, like when I showed you logistic regression, I didn't do it for analysis. I went to Cox model right away. So I kind of created an example. But we can see the days on ICU, number of surgeries and ventilators, continuous variable, give kind of a little bit better prediction. And I explain you why. When you're using continuous variable, we're losing less degree of freedom. Yes, if you listen to my lecture about distribution, I talked about what is degree of freedom. And for when you have categorical variable or divide your data, you're losing more degree of freedom, and it can affect the power of your estimate. So if you can use continuous variable, it's better to use continuous variable because at least it's not reducing a power of your calculations. So it's maybe explanation that Cox model here is predicting, like giving us more interesting stories that logistic regression before. But what should we do? We need to check the assumption. And the main assumption for Cox proportional hazard model, the hazard that our baseline hazard is proportional. So basically, based on multiplication, it's each time it's increasing at the same multiplicator. So how you doing? When you run your adjusted model, you exporting your Schoenfeld residuals to the data. It's how I do it in SAS. And after that, I do analysis on the residuals, look at the correlation. So basically, in SAS, it shows me Pearson correlation, it's p-value. So basically, if p-value is not more than 0.05, it means we don't have evidence of violations. So those characteristics kind of changing over time with proportional hazard. But you can see that bowel inhalation injury and all days on ICU number surgeries and days on ventilator, it's strong violation because it's very, very significant. And we have diabetes that kind of not here, not there. So basically looking on this one, we say like, wow, we cannot use Cox model because like about half of our predictor violating the assumption. But bear in mind here, except on age, all the variables that violate the assumption, so except inhalation injury, yes and no, those are continuous variable. And I'm not sure how to explain it, but usually it's how it is. Maybe because like you're looking for 1 point increase and like, for example, total number of surgeries, we're saying like it's between our start and end date, but it's not necessarily was distributed because someone sick and got like 5 surgeries in the first day, and after that no surgeries was done. And for example, another patient got to the hospital, everything was fine, but suddenly there was an infection and he needed to go to hospital. So if you're looking on it kind of intuitively, it makes sense. Yes, inhalation injury, technically, I don't know how to explain, like why it's not significant. But I say because inhalation injury is binary variable 1 and 0, and assumption violated, the first thing you need to do is basically to look to stratified model for inhalation injury, yes and no, and see and check assumption for each model separately to see if there is difference between two groups. So what I did here as example, I tried to plot the Schoenfeld residuals only for bulks and bulks multiplied by length of stay. It's one of the way to reduce, to make proportionality assumption works. It basically look on interaction of the variable we have issue with and multiplies by time, yes, and see if it's improved model. So this is basically I did. I took very simple model. It's died versus survived, our BAO index and our BAO index with interaction of time. So on the left side, it's kind of plot how our residual should look. So basically, if you do an assumption check and you see something like this, it means your assumption is fine. But if you look on the right side of the plot, where on x-axis you have LOS and then y you have bulks, you can see that there is some trend. Yes, it's not like randomly around flat line. There is some trend. Basically, this is what showing us that assumption is violated. So here, what I said, what I did next, I ran an adjusted model for inhalation injury, yes, and inhalation injury, no. And I got some results. I'm not going to go into details, but like things are statistically significant. And you can see that some of the estimates like more significant, some less, but there is no lot of difference. Like sometimes effect much higher, sometimes lower, but for both inhalation injury, not the results looks more or less similar. And what I did when I did exactly the same. So in here on the bottom, you can see my interpretation. Yes. So basically, BAO index or more days on ventilators will increases hazard of dying. And for having inhalation injury, borderline protective effect was fine for his ICU. Everything else like didn't change much. So what we're going to do next. So here I showed how to check assumptions like for full model. So basically I have our initial model not stratified and I plotted residuals. So basically on y-axis you will see length of stay in the hospital. On the y-axis you will have residuals, and you see the plot when the model adjusted for all the covariates. Yes, and here on the right I put the same plot still from before, like classical, how it's supposed to look. So actually, in my opinion, is not too bad. Yes, you have some kind of slow trend, but points around our trend line kind of distributed more or less equally. Yeah, the trend is a little slow, and here I summarize our plot of residuals, like our model adjusted to everything. So I say trend in residual, upward trend. Yeah, we see the regression line going slightly up. Spread of residuals, it's slightly increasing over the time. So regression line behavior, not flat regression line, indicates time dependency. And residual clustering, we have residuals, more residual clustering in the beginning of our trend and less later. So I basically put here severity. So trend of residual spread and regression line, it's kind of moderate severity, and residual clustering, I say it's low severity, low severity. So based on this one, I'm going to say what I said before. The life is not perfect, and you will never have all Cox assumptions for Cox model held for all variables. So you need kind of do everything by the book, look at it and say, can I live with it? Can I still present Cox model? And in this case, I think you can present Cox model, and I'm going to explain why. Cox proportional model rarely hold perfectly in real world data, because most of clinical and biological processes are not like proportional. Yeah, they can increase and decrease in different ways. Violations are common, and we all, like, if we have violation, it doesn't mean that we need like modified our models. We can try some things to see, like for sensitivity, say, oh, if those variables that don't hold a proportionality assumption and have some issue, I will include interaction with time and see how my model is changed. You can do it like to make sure for yourself that you did everything as possibly. How bad is violation in our case? I think we can compromise. Yes, it's like moderate to low, and results like in stratified model and actual model, the result didn't change much. So I think for me, I would publish this paper with Cox model, and this is what I usually write. In the paper, we can write that proportionality assumption were checked and not major issues were found. Yes, it's not perfect, but we still think I did everything I possibly could. I check a lot of things and I say, oh, this model is fine, I can live with it, we can publish it. I'm confident that this is the best model we can do. Yeah, but here I can add something else. Based on our story from 2 lectures, in both logistic regression and Cox model, we're also incorporating time of stay in the hospital. We identify the Bow risk factor is like very independent. It doesn't matter if you stratify model, if you use a logistic regression or Cox model, if you adjust for all characteristics or only selected characteristics, this measure is very stable. It's not changing much. So basically, I'm going to say here exactly the same as I said for logistic regression. I think the Bow index is very strong and almost independent predictor of injuries. So basically, if someone came to the hospital with really high index, it increases the chances to die regardless of additional characteristics. Those characteristics can slightly reduce risk or slightly increase risk, but overall, it's what predicts the death. So now, how are you going to publish it? You need to show how Bow index independently. Now, where based on 2 models, we decided that it's independent, kind of independent predictor. What we can do to show what is the cutoff point for Bow index. Like if Bow index is 50, what is risk of person to die if the person got admitted to the hospital with Bow index of 50? So what we're going to do next, we're going to do my additional very favorite model, and it's called receiver operative curve. And using the receiver operative curve, we're going to find the cutoff for bows in an adjusted model because we say it's independent predictor. We don't want to adjust bow index for anything else because we kind of prove it doesn't matter. So we will try to establish the cutoff point for bow index. So what is receiver operating curve? It's a simple graph. It's very simple, a non-parametric model. There is no lot of modeling to do. You just plot it. And how you plot it? You plotted it based on sensitivity and specificity. So usually on your y-axis, it will be sensitivity. And on x-axis, you're going to use 1 minus specificity. You can build it as specificity, just your figure will be will look like a mirror. Yeah, but it's still correct. But when you publish it, it's better to use sensitivity and 1 minus specificity. For example, if you do it in SAS, it's automatically doing it. Yesterday, I needed to do same analysis for something else. And because my Bayesian model was done in R, I decided to do ROC curve in R. The package I used actually first provided me specificity and sensitivity. So I needed to recalculate it and rebuild it slightly different. But in SAS, it's always presented classically. So how are we going to estimate sensitivity? Everyone knows, especially data scientists, sensitivity is true positive divided by true positive and false negative. So basically, it's all our positives, those we identify the node. And specificity, it's exactly the same, but we trying to identify negatives. So how ROC is done? Usually, your time to event here is not important. We run simple logistic regression. From logistic regression, we calculate predictive probability of something, and we plot in those predictive probability to try to estimate true negative and true positive. And how we're going to do it? Usually there is some kind of default threshold. Most program, I think, use 0.5. So like basically, if your probability from regression model is 0.6 and you choose your threshold in 0.5, it means you identify it correctly. I think correctly. Yes, so basically for this specific analysis, I ran logistic regression and I told SAS plot an ROC curve for me from this logistic regression. And in this logistic regression, we had our outcome is this, and our predictor variable bow index, it's not adjusted to anything. So what you're going to do, you plotted the straight line between 1 and 0. It's like, it says, oh, if everything was chosen as false positive and negative or chosen in random, this is the line we'll get. If you have something about this line and like strongly about this line, it means whatever happened in our model, it's not a random. There is a sense in the model. There is like meaning of what we're doing. So, and how you choosing the cutoff point if in an adjusted model? You're using something that's called Yunden index, and it's very simple. You calculate J Yunden statistics, it's sensitivity plus specificity minus 1 in each point. And basically for each point of sensitivity, specificity, you calculate this J statistics. And you use sensitivity formula, specificity formula, calculating J. And J range usually from -1 to 1, when 1 indicates perfect test, and 0 means no discrimination. So how you doing? You choosing the maximum index. So basically, on each in your data from each combination of sensitivity specificity, you calculate the J statistics, and you choosing the maximum. And from your model, based on this maximum, you can calculate the cutoff point. So here, the maximum Yunden statistics showed me that my sensitivity is 0.91. My specificity is 0.78, and the cutoff point of bow index associated with the sensitivity specificity is 77. So basically, it's say those that came to the hospital with a bow index 77, they have higher risk of dying, chance of dying. So here, what else you do when you present a ROSI curve? You need to calculate area under the curve. And in our case, our area under the curve is 0.91. So it's very high. It means our model fit is very good. It's working well. So how you can interpret this bow index? So we have our area under the curve of 0.91, and it's excellent discrimination. The bow index is highly effective in this. So, but in this case, it shows us how bow index is effective to distinguish between those positive and negative. Remember, based on sensitivity, specificity, we will have some percentage of false negative or false positive. Yes, but it shows like in which magnitude. So for this model, prediction of death for bow index, of course, was statistically significant, and optimal cutoff was 77. Sensitivity 91 says that model correctly identified 91% of actual positive. Yeah, so basically we calculated predictive probability and we look at the cutoff and both shows that it's positive. And specificity was 0.78. So you will never have situations that you have like sensitivity 91 and specificity 98. Yes, there is always trade-off between sensitivity and specificity. There's a lot of models when you can have very high sensitivity and very low specificity or opposite. So it will never be perfect, but usually for good models, sensitivity and specificity will be slightly different, but relatively close to each other. So 91 and 78, based on my experience, it's very good combination. And specificity basically says to us the model correctly identified 78 of actual negative cases. Yes? So we have high sensitivity. We have not high, but good specificity. So, and we see the bow index is strong predictor, but there is some misclassification can occur. And why? For example, one person can come to the hospital with very high bow index and survive. It's not necessary that everyone that come with bow index above 77 going to die. Yes, some of them are going to die and some of them going to survive. So it's why it will be not like 100% sensitivity and specificity. So after that, how you show it? So basically, you remember in logistic regression for each bow index point, for each participant in each bow index point, I calculated the probability, predictive probability of bow index to predict death, and I plotted it. So red value is predicted value and green lines are confident intervals. It's good to present. You can see as higher bow index is as larger confident interval is why, because you will have majority of the patients that came to the hospital probably had relatively low bow index, and proportion of those with high index were relatively small. It's why confident interval is increasing. You can see as the bow index increases, the probability increases. Also, if you listen to my logistic regression lecture, the shape of bow is like S curve, that it's how curve for logistic regression is going to look. So everything is fine here. So you can see I put the blue line here that where approximately 77 is. So you can see the probability of dying up to point of 77, it's like very low, close to 0. And around 77, it start to increase. But after 77 and between 70 and 80, let's say, it's increasing like really rapidly. Yeah. So it also shows that our cutoff point of 77, it's good. Yes. So you have still very low probability of dying with low bow index. And your probability is not one with high bow index. But we can see that after point of 77, our probability started to increase rapidly. So everyone that came to the hospital with the bow index above 77, the probability of dying will be much higher with each point of increase of bow index. So basically for this specific project, what's going to happen when basically what I understood, so when the person is going to come, based on this model, they have this plot of Bow index for is the overall of which group. You can do the same for Bow index for inhalation injury, not inhalation injury, and different one calculate kind of cutoff point. And based on those ones, they can tell patient and family of the patient like what chances. So if someone comes with Bow index of 160, like very high, they can say like, yeah, probably is like there is still chance by miracle someone survive. It's always a miracle in our field, but the chances that this person is not going to survive is really high. So basically, in summary, again, our detective was good, I hope, and we talked about everything I told. So we looked at this, how to use descriptive statistics and create Kaplan-Meier curve. I also explained the actual calculation. We looked how to compare Kaplan-Meier curves. We looked what proportional hazard model is. We looked on some of the how to check the assumption, what to do with assumption. I showed you like outputs from the real data and give my explanation. But bear in mind here, it's like I explain the story based on how I as statistician understand it. You can have different statistician with same data that might do something different. It's sometimes subjective, like for example, if you tell me, Sabrina, you need to choose between logistic regression and survival, I probably choose survival because I think the model is better because it's incorporating time in addition to all other covariates to predict outcome. But in statistic, like, you know, one of my first lectures, I talked that there is like, in statistics, there's always uncertainty. Yes, we cannot measure everything, and it's why we have p-value, because we always predict something incorrectly. We can reject a null hypothesis incorrectly, but it's kind of how you feel, how comfortable you feel with your results and present your results in the same way. For example, for this specific analysis, basically logistic regression and Cox model regression told us kind of similar story, and I would expect it and if model done properly, but the slight change just because in Cox model it's different model and we incorporated time. But basically our storyline was the Bow for both confirms that Bow index is probably independent factors that predict person death. Thank you. So are there any questions? Are there any questions in the chat? You can also, if you don't want to put questions in the chat, you can unmute yourself and ask. And also, if you didn't understand something or need to review the lecture, it will be available. It will be available shortly on our YouTube channel. You can always review it and come to meet with me and ask you questions, or if you run a specific analysis and have question about specific analysis related to what we just discussed, you're also welcome to send your questions to me.
Perfect, Sabina. Yeah, there's no
Yeah,
questions.
so I don't
so
see
far.
any questions here. But I think like people usually have questions when like I have questions usually when I do something myself. Yeah, like you question yourself. So maybe if you try to